These are magnetism concept questions, number 31 through, let's do 31 through 45. The first one says electric current can be best induced in a wire by moving a magnet up and down near the wire. Now, this one can be a little bit confusing, so what I've done is I actually have for you a little demonstration so you kind of see what that looks like. So I just got to find the demonstration. Here it is. And if I take this magnet and I get it near the wire, okay, if I take it and, whoops, it's not letting me do it here. If I can take this magnet and pass it through the wire, you'll notice that the light bulb lights up. So I can actually move the electrons through. So you'll notice even just one end does it. I can do it with the other end. You'll notice it goes down that way and goes back up on the north. So here the north will make it go down when I go to the right, south will make it go up. South will make it go down going to the left, and north will make it go up, so you can kind of go back and forth. It's kind of how a generator will work, same type of thing. So if I turn water on and turn a little wheel, I can make the north and south ends of the magnet interact with the coil, and you actually make what we call alternating current. So that's your little lesson in generating electric current in a wire using a magnet. For number 32, a magnet is moved in and out of a coil wire like we just saw, connected to a high resistance voltmeter. If the number of coils doubles, the induced voltage also doubles. This is the equation that we'll use, and we see that N is the number of coils. This is what we call flux, and we're going to divide it by time. But the big thing here is we just make sure that when we double N, we can also double the potential difference or the voltage. So if I double the voltage, double the number of turns, then I can also double the voltage. For number 33, a magnet is moved in and out of a coil wire. So here we go, connected to several lamps. If the number of coils is doubled, it is harder to move the magnet. There's more of a force on that magnet itself. Makes it a little bit harder to actually move it. For the next one, we have the phenomenon of inducing voltage by changing the magnetic field around a conductor. This is just a definition. It's called electromagnetic induction. So now you know a really big term that really doesn't mean much. We're just making a magnetic field around a conductor and just by trying to create some voltage. For number 35, a device consisting of a coil that is mechanically rotated in a stationary magnetic field is called a generator. This would be where there'd be a magnet, and as this would turn, okay, I'm turning a coil, and you end up making that thing go. So kind of the same type of thing. A generator is used to light a light bulb, so we're going to get these out and we can play with these. These are little called GenCon generators. They will light up a little bulb. That'll actually burn it out if you go too fast. Energy for lighting the bulb actually comes from mechanical input to the generator. So when you grab a hold of this and you turn it either clockwise or counterclockwise, works both ways, you're providing mechanical input, which then changes to electrical input by using the little motor slash generator on the inside. For number 37, a magnetic field strength inside a current carrying coil will be greater if the coil encloses an iron rod. So this iron rod is inside of this coil. There's tape here, but you'll see that there's some wires going into this and then they're wrapped around that coil. So we can make that magnetic field strength within that coil stronger just by adding this little iron rod. A device that transforms electrical energy to mechanical energy is called an electric motor. So I could hook up a power supply to this. It'll make this motor turn. It's got all kinds of parts in it, and then it has a drive pulley on it. So this might come out of a Prius, or there's somebody that's built a little car for us that we're going to look at. It's an electric go-kart, and works on the same type of thing. Number 39, if a magnet is pushed into a coil, voltage is induced across the coil. So you saw that in the little demonstration we had in the FET demonstration. If the same magnet is pushed into a coil with a greater speed, so we're doing smaller time, faster you go, the shorter amount of time it takes. If I decrease this, I now increase the voltage. So that's why your answer is a larger voltage. If I make the time smaller, when you divide 1 by 1, you get 1. But if I take 1 and divide it by a half, I actually multiply it times 2. same type of thing, and that makes your V even bigger. For number 40, the principal reason voltage is induced in the loops of a generator coil is that the loops are rotating, and that changes the amount of magnetic field, and when you change the amount of magnetic field within the loops, you make voltage. So when we turn our little generators, turn the handles of the generators, we are changing the amount of magnetic field. Most commercial generators are driven by steam. This is one that's driven by water. This one's driven by steam. So the steam actually comes in and grabs a hold of these little blades, and then it's forced out another end. But as it does that, it actually turns and creates electricity. So that's a commercial generator. For number 42, a device that uses two coils around an iron core to change the voltage across a circuit is called a transformer. This is a big transforming station. Sometimes you'll see transformers on telephone poles. So if I just draw a telephone pole here, that's not a very good telephone pole, but you usually see a little black box, a little kind of round, and then you'll have some wires that are going to that, and then on the end you'll see the wires go off. This is a transformer. It either makes the voltage bigger or makes that voltage smaller, one of the two. And if you open up this transformer, all you would see is some wire that is wrapped around this core, and you'll notice that there are smaller number of wines on this side. So I'm going from a very high voltage to a very low voltage, so we call this a step-down transformer. For number 43, in an electromagnetic wave, the electric and magnetic fields are blank to each other and blank to the direction of the wave motion. So they're actually at right angles. You can see the purple is the magnetic field, the yellow is the electric field. They are at right angles and they are perpendicular to the wave motion. So the wave motion is this way. You'll notice that they both go up and down or left and right, just perpendicular to the motion of the wave. For number 44, if the primary coil of a transformer were connected to a DC power source, the transformer would only operate when you're connecting or disconnecting it, because the key here is only AC power sources can be converted. And the only way to make DC AC is to connect and disconnect it. It's kind of a goofy way of doing it, or a goofy way of thinking about it. For number 45, this is the last one we'll do in this series. A transformer works because I'm basically just changing a magnetic field. A changing magnetic field is transferred to a coil via an iron core. So remember, there's a magnetic field that's generated by this coil of wire that then transfers to the other side and then makes voltage come out of this other wire. It gives it a push for its electrons. One more video after this one.